Hello everyone. Today we are going to discuss another very interesting question, and this question has been taken from the book The Cracking the Coding Interview. And this is a very common question, but the approach here implemented is really fascinating, and it is quite a different approach. Let's see how the question goes. So we've been provided an array A that contains the integers from 0 to n, but one of the integers is missing. So from 0 to n, there can be one integer which is not there in the array, and we cannot access the entire integer in the array. So for example, if I have an array 1, 10, 5, 6, 4, it is not allowed for me to do an operation like a of 1, and this will not fetch me 10. So this operation is not allowed. Rather than this, what operation is allowed is I can go ahead and fetch the jth bit in the integer ai. So if 10 is there, 10 has been represented as 1010, and I can do an operation wherein I can fetch uh, it can be like fetch second bit in uh, a of 1. So this will render me the result as this one, 1, indexing from this. Okay. So this operation is allowed, and this is a constant time operation. And we have to find the missing number in big of n times. So here I have taken the representation from 0 to 10, and also have taken the representation from 0 to 9. So here 10 is an even number, so that's why I have taken this, and here 9 is an odd number, that's why I have taken these two numbers. So let's see how the representation goes around in even case and in odd case. So let's see what are the total number of zeros in LSB. So LSB is this, the least significant bit, and this in this representation. So these two these two columns we'll be considering and seeing like how the zeros and ones are populated in those two columns. So let's find out the total number of zeros in the LSB in n equal to 10. So in n equal to 10, I can have 1, 2, 3, 4, 5, and 6. So 6 times 0 occurs. Also, I can see that in 9, it occurs 5 times. Okay. Now, in for ones, we will see how many times are ones occurring in the LSB when n equal to 10. So 1, 2, 3, 4, 5. So 1 occurs 5 times, and here it also occurs 5 times, right? So we can see that count of zeros is always greater than or equal to count of ones. This is an least significant bit, okay? Observation 1. So this is the case. So whenever I go ahead and, for example, one of the numbers is missing, let's say 4 is missing here, this is not there, then what will happen is the number of zeros will be 1, 2, 3, 4, 5. If 4 is missing, I will have zeros 5 times, and 1 will also be occurring 5 times. So here, if I say that the least significant bit of the missing number is 1, then the count of ones will be 6, which is not possible because I have already observed that the count of zeros can be equal or can be greater than the count of ones. So here I can be sure that the last significant bit in the missing number is 0 itself. It cannot be 1, right? Now let's go ahead and see if this applies to the odd number also. So if the missing number here, let's say it is 7, then what will happen if to the least significant bit? Zeros will be occurring 1, 2, 3, 4, 5 times, and ones will be occurring 1, 2, 3, 4 times, right? Let's say I increase a 0, then count of zeros will be equal to 6 and count of ones will be equal to 4. This is having a difference of 2, which is also not possible because here I already saw that count of zeros, if it is greater, then it will be greater by only one value. So this is not possible. So I can say that it should be a 1 that is in the missing number. So when I have a 1 in the least significant bit of the missing number, what will be the count? The zeros will be occurring 5 times and ones will also be occurring 5 times. Now we know which is the which is the least significant bit of the missing number in both the cases, when n is even or when n is odd. Now we already found out the value of the last significant bit in the missing number. Now let's go ahead and see the second last least significant bit in the missing number, that is this column. So in the previous case, I had considered the number 4, which is missing, and here I had considered 7, which is missing. So in both of these cases, what will I do next is, if the least significant bit is 0 here, I don't have to consider all the numbers which have the least significant bit set as 1. So I can remove this, I can remove this, and this also. Okay, and similarly here, if the missing number was 7 and I already found out that the least significant bit is having a 1 value in the missing number, I should not be considered about the digits which have 0 at the least significant position. So in by the similar observation, I can just deduct all these numbers. Okay, now let's do the same operation that we did before. Count of zeros, ones in 0 to 10 and 0 to 9. Now here I'll be considering only the numbers which are not striked out in the upper tables. Let's see what are the number of zeros in the first table at this column. So number of zeros are 1, 2 and 3. And number of ones is 1, 2 and I guess 3. Right? And similarly, what I can do here also, number of zeros is 1, 2, 3, and number of ones is 1, 2. Now again we can observe that number of zeros is always greater than or equal to number of ones, and if a number of zeros is greater than number of ones, then it will be just with the number of zeros will be equal to number of ones plus 1. So this is the only difference that we observe. So via this observation, let's see if it adheres to our observations or not. We already saw that 4 is missing and here 7 is missing. So if I remove 4 for a while, then and here 7 for a while, then what will happen? The number of, let's find out number of zeros in first table and number of ones in first table. I'm not considering 4 here because it is missing. So while solving this question, what we'll do, we'll find the number of zeros at this particular column. So number of zeros is 1 and 2. Number of ones is 1, 2, 3. Right? So if I increase the number of ones will be greater than number of zeros, which is not possible. So this significant bit is a 0 here, which is the case. So this is the 0 here. Also, let's consider the table where 7 is missing. So number of zeros is 1, 2 and 3, and number of ones is equal to only 1, I guess. That's right. So if I increase number of zeros, it will be 4 and the difference will be 3, which does not comply with this observation. The missing number is set. So here I can say that the least significant bit 2 is equal to 1 here, and LSB 2 is equal to 0 here. Now you can do it iteratively and find all the bits of the missing number, and at last you will be left with the number. So this is the solution for this particular problem. Let me know in the comment section below how do you like it, and if you really liked it, please consider liking and subscribing to the video. Also, if you have any questions, please feel free to comment down below. Thank you so much.